Just waiting for some people to file in. So thank you so much for those who have already answered the poll question. Just let us know where you're joining us from. All right. Well, it looks like we're almost coast to coast this time, Gord. From Alberta to the Atlantic provinces, many from Ontario. So it's almost
Only a
coast to
couple
coast.
there.
Yeah. Hey, but I'll count it. I'll count it. Here, I'll show you here. Share the results so everybody can see, mainly from Ontario, but also from Alberta and the Atlantic provinces. So welcome, everybody. I'm going to ask you one more question. We would like to know, what occupation are you in? So let us know here. So I think I've covered all the different occupations, or most of them. And if I didn't, if I actually didn't include your occupation, that would fall into the other. And let us know in the chat what it is that you do. I have to say, where I'm at in Southern Ontario, it is a beautiful sunshiny day finally. So hopefully that's that's the same for many of the others. Let's see. All right. Looks like almost everybody's responded. Okay, thank you very much. I'll share those results. So it looks like we've got representation in all the groups, including some in the other category, with many of them being in trades and construction and engineering and architecture. Well, excellent. Thank you so much. I'll just stop sharing that. So welcome, everyone. My name is Stephanie Coleman, and I'm with Building Knowledge. And so I want to welcome you to our Advanced Building Science webinar series that is sponsored by Enbridge. And today, Gord is going to be talking about right-sized HVAC equipment. Susan Cudahy, I want to thank Susan and the team at Enbridge for their sponsorship of this program that is monthly. And you will see at the end of the presentation as well, I'll bring this up again. But our next event is on June the 17th, and we're running these for the remainder of the year every month. So if you have not been on these sessions in the past, we just ask, if you have any questions for Gord, just put those in the Q&A section. And what I'll do is I'll monitor those and interject every now and again to ask your questions of Gord. And if you have any sort of general comments, just put those in the chat. So we look forward to hearing from all of you. I'm going to stop sharing and I'm going to hand it over to Gord.
Thanks very much, Steph. I noticed in the chat, Paul said he was an all-around good guy, and I'll just say I'll be the judge of that. And actually, he is an all-around good guy. So good one, Paul. But you should really let me judge that as the webinar leader. So
I can create a survey, a poll question on that if you'd like.
Right. And just remind me, Steph, it's okay for them to ask questions throughout?
Oh yeah, absolutely. Yep.
And you'll interrupt me if I don't see the piece.
That's right. What I'll do is I'll just turn my camera on, just like you see now, and I'll let you choose if you have time to answer the question or not. But I think you probably will.
Right.
Yeah.
So it's 1 o'clock here in the center of the universe, and we will
Cambridge.
I have maybe just over an hour's worth of stuff, which means you can ask questions during or after. Sometimes talk too much, but by all means, there's time to ask questions. So that's
excellent.
what we'd want to think about. So let me see if I've got the right one. Yeah, I think I do. Just share that. And hold on, just got to move that out of the way. You can see my screen?
Yes, I can. Yeah.
Great, thank you. So thanks for those who've dropped in. This is a session that's near and dear to my heart. It's actually near and dear to Enbridge's heart too, to make sure that gas is used wisely, or their energy is used wisely in houses. And it does have some impact, of course, on energy efficiency. That's not going to be our focus too much today on the energy side, but on the comfort side is probably where we're going to head. This is a topic that's undoubtedly known to most of you. Hopefully I'm able to bring you some value with some new thoughts or some new thinking, but we'll head from there. Oh, that's Oh, there we go. In terms of what I thought we would discuss today, I'd like to do just a little refresher on the basics of HVAC calculations. I think it is useful to look at the math, the algorithms, to kind of, oh, that's right, I can see how that's going to work. That's going to help us with the building science connections to that is understanding the physics or the math around that. Then, of course, we want to talk about some examples of risks and opportunities and some adjustments and enhancements that you can make, and a little bit on some future considerations, if you will. So let's start with the basics of HVAC calculations. I'll start with this because I know there's a bunch of energy advisors on the call, architects and engineers. I'll remind you that much of our world, that is as energy advisors, is in a software programs, energy modeling software that would give you annual estimated energy use. Okay, so it's not looking at what's happening on any given day. It's trying to accumulate over the course of the year how much energy is being used by heating equipment, by lights and appliances, by hot water systems, and so on. So that's and as we get to net zero or down close to net zero ready, you'll notice we've cut the amount of energy roughly in half, a little more than half, if you will. Sorry, a little less than in the range of half, I guess. That's in terms of total annual energy use. So that's energy modeling. That's important. It's nice to know, but what we really want to know in terms of sizing is what's happening on the design day. That is, how big does our equipment need to be? So that's where we're going to head towards, is what equipment do we need, or what size do we need that equipment to be? So this is looking at the estimated instantaneous heating design load, and this would be referred to as the heat loss. So a couple of key words there, estimated. In the same way that we estimate energy, nobody's suggesting that that's actually how much energy you're going to use. When we estimate the heating design load, you're going to say, well, gee, I'd like to be pretty darn close. I certainly don't want to be under. That is, I don't want to be smaller than what I need on the design day. So by definition, when I do an estimated heating design load, I try to be conservative. I actually give, if there's room to play at all, I try to think about, or at least the programs try to think about worst case scenarios. So keep that in mind. When you do a heat loss, it is set up, the standard algorithms of the day are designed to be worst case. They're not designed to be necessarily accurate. If anything, they want to be a little conservative, a little oversized. And I say that for good reason, because sometimes we hear people say, well, I'm going to do the heat loss and then I'm going to add something to it just in case. No, all the just in case have already been added, and I'll try to show you that's how it works. And so look at the difference on those houses. That a house built to the typical code today, 3,000 square foot house, would need 69,000 BTUs, which is a pretty darn good number, pretty low number. But by the time we get to net zero ready, I only need 29,000 or 30,000 BTUs, basically half the size. You can say, well, that's pretty much the same as the energy. The energy was half the use. And it is useful to see that the estimated design heating load, is roughly half. Let's go to the estimated instantaneous cooling design load. That is the worst or hottest day, if you will. And that, of course, we would refer to as heat gain. In this case, it's not quite half. In fact, it's a little less than half. You'll notice here, really important to notice on this slide, look what percentage of the heat gain is associated with windows. Windows represent 45 to 55% of the heat gain. No longer, if you're trying to size an air conditioner, you almost could care less what insulation was in the walls, what insulation was in the ceiling. What you'd really not want to know is how many windows have you got, what are they made out of, and more importantly, which way are they facing. So I'm going to give you a sense of that. And you'll notice that the the design cooling day at 27,000 BTUs is very similar now to the design heat loss at 29,000 BTUs. Wow, the cooling loads haven't come down as much as the heating loads, and that's an important element. Notice still in the heating loads, that infiltration is still, or was, a big portion, and now of course in net zero houses we've made them much smaller, so the infiltration loads are only 10%. So notice those fundamental changes, I would say, in how houses work. When you get to higher and higher performance, air conditioning loads become a bigger and bigger deal, if you will, is where we want to get to with this. And big learning out of today, it's always about windows. People ask me all the time, what size air conditioner would I need for a 2,000 square foot house? I could care less the square footage of the house. Tell me how many square feet of glass do you have. For mechanical contractors on this, change the conversation over the next few months. When you get that call, you'll find it really instructive. It'll actually help you sell more air conditioners by asking them, hey, tell me how many square feet of glass. I don't know how many square feet of glass. Right, that's why I want to come to the house, measure it for you, and understand. I'll bring my compass with me to understand what orientation you're on. So keep those things in mind as you're as we talk about the rest of the day. But again, I'll say estimated, trying to be conservative is where we're headed with this. And so I always like to report on the fact on the right-hand side that we have a relatively new, that is 2012, it's actually been updated already in 2014 and again in 2016, we have this lovely CSA standard called F280 that's used to determine the required capacity for space heating and space cooling, as CSA F280. You'll hear me refer to it a number of times. And within that standard, I want to remind you, everything in there is conservative. That is, when the committee met to rewrite the standard, if there was any question as to whether we should include, the windiest days or the coldest days, it's always, yes, we're going to try to include the worst case conditions. That is, we do our heat loss assuming there are no people in the building, right? There's no lights, there's no appliance, there's no TV running, there's no people generating heat. We assume the building is empty. And you can imagine if there was people in the building and we knew that, we wouldn't need as much heating in our houses. In design cooling day, we assume everybody's at the house. We assume the lights are on. We assume the drapes, we don't assume the drapes are open, but we actually assume the sun is shining on all sides of the house at one time, as an example, which of course is totally ridiculous. But we just don't know, so we assume higher loads than what otherwise are normal. So I'm trying to give you the sense that there's safety factors built into the heat loss, heat gains, so don't oversize. Don't oversize, because they've already been conservatively oversized. But the next key learning out of today's session is this: the heat flow formulas. That is the basic algorithms that are sprinkled through. And there's a few others, but the vast majority of the parameters, the algorithms that, or the calculations that you're doing are using these three formulas. And I spend just a little bit of time on it. Conduction heat flow. That's the heat flow through solids, through walls, floors, ceilings. And it's a very simple formula. It's the surface area. It's not the square footage of the house. It's the surface area of the walls, the surface area of the ceilings, times the temperature difference across that wall, floor, ceiling on the coldest day, or whatever you determine to be the worst day, divided by the R value of that wall. Now, here's first thing we need to understand. We're Canadians. We're trying to be metric. But for whatever reason, we're still stuck on imperial in some key areas. For example, R value. We don't seem to know RSIs very well. So everybody talks about R60 ceilings. So guess what? Since we're going to keep it at R values, everything else has got to be in imperial. So surface areas in square footage, temperature differences in degrees Fahrenheit. You absolutely can adjust these formulas. The formula will be exactly the same, surface area times temperature difference in Celsius and RSI values. You could do it as those, and you could convert it. But now you would be in watts or something like that per square meter. In this case, we're doing imperial numbers. So the rest of this session, I'm sorry, everything's going to be in Fahrenheit and square footages as opposed to metric. The second big heat gain component in this case is the radiant flow. And this is specifically through transparent and translucent elements. and it's such as windows. So in this case, it's the surface area of the glass times something called the solar incidence. What's that? Well, that's how much heat we're getting from the sun. Remember, the sun is 93 million miles away, 4 trillion degrees on the surface of the sun. That heat comes to us via radiation. Some of it makes its way through the ozone layer and so on and hits us. And I'm going to show you how many BTUs you get per square foot based on what orientation you're on. And so that's what we would need to know from a radiant gain perspective. Times the solar heat gain coefficient, most of you will recognize that. That's a term that's used in windows. That's a function of the emissivity of the glass of the window, how much heat comes through it. And in terms of, if I said to you the solar heat gain coefficient of a solid would basically be zero. It has zero solar heat gain coefficient. No radiation or no light, solar radiation can get through it. So that's why this only applies to translucent, transparent elements where the sun actually can't make its way through. The radiant flow can't make its way through. The third important formula, and I'm taking time on these, take a screenshot. Steph, I can't remember, do we make these, do we make the PowerPoints available?
Yes, we do, in a PDF format.
So you'll have these, and that way all of you can correct me when I've said something wrong. So that'll be good. The third formula is heat flow via air. So think about air leakage coming into the house or ventilation. And we're also going to use this formula to figure out how much air we need to heat a space or cool a space. But in this case, it's equal to the volume of the air, the cubic feet per minute, times the temperature difference, times this constant 1.1. And this does vary a little bit depending on where you are. If you're up in the mountains in Alberta, this number would be a little different. But this has to do with the specific heat of air, the density of the air. That's all it is. It's a physics constant. It stays at 1.1 or 1.08 depending on latitude. But you get the idea. Those are the three basic formulas, and we're going to use those throughout this session to remind yourself. But you can just from straight, let's say, grade 6 math, you can start to imagine on conduction heat flow. If I double the surface area, I'm going to double the heat flow. Right. If I double the R value, I'm going to cut the heat flow in half. Oh, so if you really wanted to have a smaller furnace, you would make smaller houses, less surface area, and you would put more insulation in. You would double the R value, if you will, or triple the R value, and away you would go. So those are the basic formulas that are used in CSA F280. The only thing that, we used to do these manually. Now all of these are built into spreadsheets and we do them automatically. But this is the designed heat loads and heat loads and heat gains that we want to speak of. And just to put a little finer point on that, to give you a sense of that, if we wanted to know heat flow through the attic, say 1,000 square feet of attic floor, and if I said to you it was 70 degrees inside and 10 degrees outside, cold winter's day, 10 degrees Fahrenheit, remember, 70 degrees, that's a temperature difference of 60, right? 70 minus 10. And if the R value was 30, I'd have 2,000 BTUs of heat flow. Pretty simple, pretty straightforward. If I double the insulation to R60, 1,000 times 60 divided by 60 equals 1,000 BTUs. You'll notice we added R30 and got 1,000 BTU credit. Now, the passive house folks on the call would say, 60? What are you talking about? I don't want 60. I want R120. Fair enough. Let's do R120. 1,000 times 60 divided by 120. Now my new heat flow will be 500 BTUs. Okay, so the first R30 I put in saved me 1,000 BTUs. Then I added another R60 and it only saved me 500 BTUs, the diminishing returns. In our world, the size of the furnace would go down, the size of the heating equipment would go down by directly related to the amount of insulation that you put in the building. But you get the sense of where this is going. There's no magic bullet as to how we do this. And we see from time to time people telling us about magic heating appliances that do have some totally different heating mechanism. And I would say good luck with that. These are the basic formulas that would be used in our world. You can't make new energy out of, we just need to be conscious of these basic formulas is what we want to get to. And if I went to the wall, for example, R20, and now of course I have 3,000 BTUs because I have less insulation. Now you immediately going to ask, well, wait a minute, is that R20 real or is the R20 effective R value? And it's a good point. The early days of heat loss, heat gains, they just took nominal insulation values, the insulation value in the stud itself. They didn't necessarily consider the studs. The newest and best of heat loss, heat gains would actually ask you to build the wall. They would ask you what's the stud spacings in the wall, and it would make the calculation in the background. So you might still enter R20, but it may say yes, but I'm going to assume there's some studs in the wall, and therefore I'm going to take it down to R15, for example. The ICF folks would have a bone to pick with this. The insulated concrete form guys would say, well, our wall is a true R22. We should get full credit for that, right? So in the heat loss, heat gain formulas, you'd need to make sure and look at the software that you're using. Is there a place where I can enter the actual effective R value? So you should be entering the actual effective R value for that wall, or the algorithms within the computer program, software program, should make adjustments for the effective R value of that wall. So that's conduction heat flow. And I'll just, again, put a little finer point on that and just remind you that that's heat flows moving in the summertime and out in the wintertime. Pretty simple, pretty straightforward, right? And when you double the insulation, you cut that heat flow in half. You'll notice that the heat flow through the slab is actually always, and let me just go back to that quickly. The heat flow through the slab is always down. Even the summertime, the heat flow is moving through the slab. Why is that? Well, because the ground is always cooler than the air temperature inside the house, right? The ground, deep ground temperature, 4 foot deep, is 50 degrees roughly. Again, we have to stay in Fahrenheit, 55 degrees. So we actually get a cooling effect out of the ground. It reduces our heat gain. It reduces the size of our air conditioner to not insulate the slab. So you can imagine in the south, I was just doing a heat loss, heat gain for the south, and under slab insulation helped us in winter, hurt us in summer. And the further south you go, the more you would go, no sense insulating under the slab, because that's actually increasing my cooling load. So get a little sense of that, if you will. And then the next question becomes, Gord, you said surface area times temperature difference. How do we determine what the temperature difference is? Well, that's called design conditions. And you can find these either ASHRAE, it's actually listed in the National Building Code. The Ontario Building Code references the National Building Code. There's long-term data, weather data, that's been taken, and they're basically 30-year averages. And if you'll notice there on the right, I've shown 2 different cities. I didn't go outside of Ontario, sorry for that. But if we looked at Ottawa or Windsor, we're talking about the 99.6% day. That is 99.6% of the time over the last 30 years, according to ASHRAE and the NBC, it's been warmer than minus 12 degrees Fahrenheit. Now, of course, if you're in Ottawa, you say, well, we had a colder day than that. And you may recall the weather person always gives you the feels like temperature. They never just tell you the temperature anymore. They tell you the temperature plus the wind chill. Oh, it's close to minus 30. Okay, you're going to say, well, what number should I use? You should use the minus 12 because the minus 30 included some wind effect. And guess what? The CSA F280 standard takes into account wind. When we give you this design day, within the algorithms, it also gives us a sense of the wind that's happening on that day. There's a wind effect built into the heat loss, heat gain calculations. So just put in the minus 12. Don't put in what the weather person said it felt like on that given day. You do the 99.6% of the time. And if you do the 0.4% of the time, that's in the order of, 20 hours a year, something like that. Somebody will correct me, but 0.4% of the time is 20 hours a year. So for all but 20 hours of the year, it's warmer than minus 12. And Windsor, you'll notice, is, I can't see it. Steph, you might have to help me. I need to move this out of the way. I have all the people here. I can't see it. What's the Windsor number?
Sorry, which number are you looking for
No,
specifically?
winter design temperature. Winter design.
Oh, yes, 2.4 degrees Fahrenheit.
2.4 degrees.
Yeah.
And if you think about that, the temperature difference in Ottawa is 70 inside the house and minus 12 outside the house. Windsor's only 2 outside and 70 inside. So it has a smaller temperature difference. And if you look at the bottom of the slide, that means Ottawa is 20% colder than Windsor. 20% more temperature difference, if you will, 20% higher temperature difference. And therefore, across every wall, across every ceiling, there's 20% more heat flow across a wall in Ottawa than there is in Windsor. The second number, of course, summer to dry bulb. This is, again, 87 degrees. The number beside it is the coincident dew point. You will know what dew point is. That's the point at which we'd see condensation. On a hot day in Ottawa, the dew point on the design day, the 99.6% design day, on the hottest day, the dew point outside is 63.7 or 64 degrees. Okay. Go down one number, one row. The design humidity day, not the hottest day, but the most humid day, the day that happens, I don't know, like today. Today's actually pretty good, as you said, Stephanie. But imagine a cloudy, humid day. It's been raining and it's humid. The design cooling is only 78 degrees, which means your air conditioner isn't running much, right? It's 74 in the house, it's 78 outside. The air conditioner's going, it's not that hot out. But the humidity, the dew point, is now at 71 degrees. That means any air coming from outside that hits a surface cooler than 71 degrees, 70.7, is actually going to condense. Look at the design humidity day in Windsor, that's 73, 74. Are there any surfaces in your houses that are cooler than, in this case, 71 or 74? And the answer is lots of surfaces. All my cold water pipes. In fact, if my clients have turned down the air conditioning to 70 degrees because they like it cooler, or they're trying to dehumidify the house because it's clammy, then you're going to find, boy, I'm going to have condensation on surfaces. Of course, this is a big deal down south. It's what it's all about. Bathroom fans sweat, pipe sweat, toilet sweat, all kinds of things. Metal grills sweat. They get sweat inside of the dryers, those kinds of things. And oddly, we're starting to see a little bit of that in Ontario to understand the design dehumidification day. So keep that in mind. And if you oversized your air conditioning, here's always the big if. If you oversized your air conditioning, specifically on that day, the air conditioner would hardly be running. It would run for 5 minutes and then turn off for 55. And in those 5 minutes, we ask the air conditioner to do two things. We ask it to cool the air, but we also ask it to dehumidify. And if it ain't running very long, we're not getting much dehumidification. So your first lesson, when we say bigger is not better, it's primarily directed at air conditioning. Air conditioning doing this dual function of trying to do dehumidification. And if your air conditioner is your dehumidifier, A, don't oversize it, or B, stop asking it to be your dehumidifier. Find another way to dehumidify. The next two lines down give you a sense of how cold you are for how long. That's degree days heating and degree days cooling. These are numbers that are not used in a heat loss heat gain. That is, we don't really care how cold you are for how long. We just need to know the 99.6% day. These degree days are used in energy modeling. They're not used so much in heat loss or heat gains. But then I mentioned solar incidence. And here is in Ottawa and Windsor, and you go, well, they're about the same. That's right, because they're basically the same latitude. These numbers only vary significantly based on latitude. But in Ottawa, a south-facing window, 50 BTUs per square foot. What's a BTU? A BTU is basically a candle or a matchstick. So on a sunny day, if you will, if you went down to Mother Earth or on the patio or something, and you measured the amount of BTUs that with the sun, a BTU meter, watt meter, BTU meter, you would see that per square foot you were getting 50 BTUs of heat. Think about 50 candles in 1 foot square. That's the amount of energy that's coming from the sun. On west facing, in the afternoon, obviously, late in the afternoon, as much as 90 BTUs. Notice that increase, almost double the amount of energy on a west face. You get to see where this is going and how difficult this is, especially since every one of your customers wants more and more windows, and apparently they never want to put, or they never expect that there's going to be curtains or blinds on those windows. So there you have it. That's the solar incidence. These become the base design numbers for all of the rest of the work that you're doing in heat loss, heat gains. And I'll give you a little sense of what that looks like. Our next little piece, thinking building science connection, is the convective heat flow, if I may. Convective heat flow. Warm air rising, cold air falling. And the amount of heat loss or heat gain, if you will, associated with that is the volume of air that's leaving times the temperature difference divided by, times 1.1. The problem with that equation is we don't know the volume of air on any given day, right? We don't know, and that's the algorithms try to predict, and they use what's called the Alberta infiltration model. Unlike the heat loss, heat gain through walls and ceilings, that was basically Sir Isaac Newton that gave us those formulas hundreds of years ago. The amount of air that leaks out of a building, boy, that was Harold Orr back in 73 that started to figure out how much air is leaving a building on any given day. And they did a whole bunch of study in Alberta and figured out, based on pressures and so on, how much air might be leaving a building. You'll notice immediately from a heat loss, heat gain perspective in the wintertime, some rooms are really impacted, that is basements and first floor. And some rooms, if anything, actually benefit from this, that is they're getting the heat from below. So in terms of heat loss, heat gain, or heat loss, the bottom level of buildings actually needs more heat than the top level of buildings on a cold winter's day. And you'll notice there the line, the neutral pressure plane. Of course, this changes on a day-to-day basis because now the wind is blowing, or now you turned on a fan. And this is by no means static. So the algorithms have to assume what? Well, they assume a cold winter's day, they assume it's night, and they assume in this case there's not a lot of wind impacting because they want to do the stack effect in this case. So this is an important one. And so just as a little example, I always like to show the house on the left. That's the ubiquitous starter home that we have, about 5 million of these across Canada that look like this, that were built for our heroes coming back from the Second World War. And this is not the house my mom and dad lived in, but it's similar to. It's just down the street from it, and one of the last ones that hasn't been fixed. And you'll notice it's not a very tall building. There wasn't a lot of stack effect. So that's the 1,200 square foot starter home. On the right-hand side, that's the 1,200 starter home today. The 3 stories of staircases, 1,200 square feet of staircases is what you bought. And this is slab on grade, which means those bottom levels are seeing lots of air leakage. And what you need to know is per story of building on a cold winter's day, roughly across Canada, it's about 4 to 6 pascals of pressure per story. So that 3-story building is seeing a positive pressure of upwards of, this actually was from Winnipeg, this building, that the top level of that building might be seeing 15 to 20 pascals of positive pressure, air wanting to leave. 15 to 20 pascals, that's in the order of, I'm going to say, a 10 or 15 kilometer an hour wind. 10 to 15 kilometer an hour wind that's pushing air in at the bottom and pushing air out at the top. And that's one of the reasons why that little front entryway is always so cold, is any air leakage you've got. So why do you want to make houses tighter? Because from a heat loss, heat gain perspective, it makes that building much easier to stay comfortable when I limit that stack effect. And what you need to know is heat loss, heat gain software never used to take this into account. Never used to. And most, let's say the US program, still doesn't take this into account. It does, at least on the residential side. Well, Jason might correct me on that one, but as far as I recall, Manual J does not ask you, nor does it may ask you what floor you're on, but it doesn't adjust based on air leakage. So this is important for us to understand. And again, in the trend, of the topic of the day, bigger doesn't necessarily mean better. It's not about the whole house in this case. It's about dividing up where the air should actually go to counteract these elements to make sure that we're going to be comfortable is where we want to get to. Good. So
Lord,
I just, sorry, question?
could I interject with a couple of questions?
Yes.
Okay, so a couple of them are from much earlier in the presentation. And so
Sure.
the first one is, does the cooling load take into account humidity?
It's a great question, and the short answer is not really. What it does is that certainly the CSA 280 standard simply says add 30%. So it tells you to do your standard sensible loads, and then it says, on average, people are this amount, that amount. So add 30% to whatever your load is. That is a little bit magical because it turns out most air conditioners are sized to be roughly 30% of their capacity goes to removing latent. So there's a little bit of deference to that. But you should, in fact, could start doing an actual latent load calculations for specific clients. For example, if you have a client that says, I have a grow home here. I grow medical marijuana. All right, I better do the latent load. I need to know that. And certainly in the southern U.S., the big task we have is actually doing the latent load calculation. How many people, what's the air leakage, and so on. But so the short answer is F280 does include latent, but it's a simple 30% factor that it adds.
Okay, thank you. The next question is, where is ventilation on the cooling design pie graph for the code built house?
Let's go back to that. You were asking on the cooling. It's a great point. On which one again? On the 3,000 square footer.
The cooling design pie graph for the code built house. Yeah.
Yes, and it's not there. You're right. I think it's lumped into infiltration. You're right. That's a flaw. Maybe I didn't put it in as ventilation. That's a flaw. Thank you. Thanks for pointing out my flaws. My kids are good at that, and apparently people on this call are good at that. That's great.
Oh, no, it's all good. It keeps us on board.
Yeah, I'm kidding. Is there another question?
Yes. So does the building conditions take into account elevated temperatures in attic spaces in the summertime?
Ooh, another great question. And what we've learned is no, it actually doesn't. We assume that the attics are ventilated. And you're going to say, Gord, you just said they did it conservative, and now you're telling me it doesn't include that. And you're right, it doesn't. Nor does it include the slab edge being heated up on that multifamily building. It doesn't do a very good job of understanding that the radiant heat or the warming up the edge of the slab. So it doesn't take into account how a brick house heats up because it assumes the brick is vented. So I said they're conservative, and in this case, actually, they're not conservative. Where it would come in is if you had ducts in the attic, you would be asked to show the duct losses. So you would put in a calculation for the duct losses due to ducts being in the attic space. So that is a piece that you can put into a heat gain calculation in F280, but it does not increase the temperature of the attic in the summertime. Now, the good news is the temperature in the attic, or at least the heat gain across the attic, because we're doing our 50, our 60, it's not very much anyway. You'll see here in a minute, it's more about windows, so we don't really worry about it too much. But good question.
Okay, so the last question was if you could just go over again the dew point versus the dry bulb dew point again.
Yes. So let me see if I can. I'm not exactly sure what they want, but if you think about the temperature on the thermometer, that's called the dry bulb. The actual temperature on the thermometer that's outside, not in the sun, so it's in the shade. It's measuring the actual temperature. The dew point temperature is the temperature at which you would get condensation, and it's a function of the temperature of the air and the amount of moisture that's in there. That is the relative humidity of that. And on the hottest days, it's actually not as humid as you might think because it's hot. And as you know, if you warm air up, it expands and its relative humidity goes down. So the design cooling day, that is the hottest day, actually almost always has a lower dew point than the design dehumidification day. Of interest, that design dehumidification day is not in the National Building Code. It is in ASHRAE, but only in the last 10 to 15 years. That is, we never used to think about this. And in fact, heat loss, heat gains do not take into account the humidity outside. They actually don't. They just apply that 30%. They do not look at the humidity outside as being part of the cooling load. So hopefully that answers it. I can, if that's not satisfactory, somebody send me an email and I'll answer it in more detail, or make you do a psychometric chart exercise. That's another webinar, right? We're doing one on moisture at some point.
Yes.
That's the one. Tune into the psychometrics one and we'll really do that one. Good.
The last question, which I know
Yep.
I think you're going to touch on, so I'll just read it to you and then you can address it.
Sure.
Excuse me. Does internal blinds inside the building envelope decrease the solar heat gains?
It does, but not as much as you'd think, because the blinds actually do warm up. The surface of the glass warms up, the blind itself warms up, the airspace between the blind and the house warms up. So yes, you get a shading effect, absolutely, and you want to show that. Our heat loss, heat gains assume that windows are shaded with blinds, but it doesn't reduce it to zero, because there is still there's still a little bit of heating up of the various surfaces. So hopefully that answers. Good. So I mentioned F280. I'll just move along here a little bit. The new heat loss heat gain standard as of 2012, it recognizes measured air tightness, which is great. Obviously, you have to be able to predict, and people ask me, how do I predict? Well, builders have a pretty good track record. Pick a conservative number. I always get under 2 air changes. Give that to your HVAC designer. That's fine. The new heat loss heat gainer gives a much better accounting of new windows and new coating options. We would say it's much more realistic and cost effective, and it does recognize air leakage on different levels. It recognizes the fact that rooms on the main floor need more heat than rooms on the third floor, for example. So that's kind of useful. And here, just showing that you can put in the final numbers, and as good as you can get, I would encourage you all to ask your mechanical designer, or mechanical designers ask builders, what are your blower door numbers? What are you willing to commit to? Let's use an actual number, because it does remove uncertainty in heating and cooling mode. And it ultimately improves moisture control when you make houses airtight. So make sure you're doing that. I just wanted to show you an example of what happens if you start fudging numbers. So there's the actual, right? The -12 and the 87. But if somebody said, well, it's cold here, and I put in -22 because we got to -22 last year, and it's getting hotter, global warming, I'll put in 95. And our indoor design temperatures, you could quibble with this one. Let's be really clear. A heat loss, heat gain is done assuming 70 degrees, 21 degrees Fahrenheit, 70 degrees. Some have changed it to 22 Celsius, so 72, but nonetheless, 70 degrees. And the design cooling day, the inside design is 75. And many of you will say, my homeowners want it cooler than that. Well, then I guess you should design for cooler than that. But it is designed for that. But if you put it in at 72 and 72, and so on down the line, if you assumed worst case, east facing versus the actual, which was north facing, if you didn't use the right solar heat gain numbers, for example, you just use the default numbers that were in the software. If you didn't do the right air change, I just want to show you the difference that you would get. You're going to say, well, each one of those are small incremental changes. Right, they are. But look at the difference. There's the house that we were doing it on, by the way. And there's the difference between the assumed data, says 80,000 BTUs, 79,000, and the actual says 49,000 BTUs. This isn't anything to do with the amount of insulation that's put in the house. This is just an HVAC designer not putting in the right numbers. And I know nobody on this call would do this, but I'm just showing you the implications it has. It's not quite twice the size, but it's certainly 2 furnace size up. Instead of a 50,000, you're putting in an 80. Oh, and that is a good point. Knowing that you have a heat loss of 49,000 BTUs, what size furnace should you put in? Well, you got to put in something that gets you at least 49. And it's totally fine to oversize it by 10 to 15 to 20%. So that means a 60 is just nice. There's nothing wrong with a 60,000 BTUs. You're going to be just fine. No need to go to a 75 or an 80. 60 is going to be fine. The one on the right, the 79,000 BTUs, well, 80 is a little light, so I'm going to go to 100. And if I went to 100,000 BTUs, because I'm oversizing slightly, and the actual heat loss is only 49, the furnace is actually bigger, twice as big as it needs to be. So oversize by furnace selection, don't oversize by fudging numbers, is really the point. And of course, somebody's going to say, but I need a larger furnace, a larger air handler in order to get me my cooling loads. Well, here's the problem. Remember, the windows were 50% of the cooling loads, and if you had the wrong solar heat gain in. And this is pretty important because in Ontario, anywhere in Canada, you can get basically at the drop of a hat from any window manufacturer. I don't know if there's any window manufacturers on the call. They can get you about 4 different coatings, anywhere from about a 0.22 solar gain up to about a 0.64 solar gain. 3 times the solar gain between basically the same type of glass. Well, not same type, same look of glass, if you will, 3 times the solar gain. And notice what happens. The heat gain is double. Heat gain is double. So what's the appropriate size on that house? Well, 22,000 BTUs. You could actually go 1.5 tons. 1.5 is a little small. Go to 2 ton. And if you said, yeah, but I really want to be safe, I want to go to 2.5 ton. I'm actually okay with that. 2.5 ton is fine. Oversize a little bit. Just don't put in a 3 or 3.5, or in this case, this is showing 3.5 tons on the right-hand side. So that we need to be really careful about not oversizing, which really means everybody on this call get to know each other and share the important information, the insulation levels, the window data, the house air leakage. And builders on this call, be really careful about the windows you choose and make sure that your HVAC designer has tried them. Have them do a what if. What if I put in a slightly different window, and understand that. And window manufacturers, if you're on this call, be true to this. Don't be switching out based on these numbers. This is based on let's say cost numbers. Let's make sure that we are everybody define it. And frankly, I don't care if you use a 0.6 solar gain. I just need to know if you're going to use a 0.6 solar gain, because you're going to end up buying a bigger air conditioner. And whatever you saved on the windows might have cost you on the size of the air conditioner. You're going to say, well, I don't put the air conditioning in. My homeowner puts that in. Well, what a shame that is, that you're telling the homeowner, yeah, we're going to make you spend an extra $500 on your air conditioner because we put in a piece of glass that saved us 22 cents or whatever that happened to be. So I just want us to be clear on that. Our second little piece, and we've already kind of done it, is the building science and the HVAC connection. And clearly, high performance homes reduce heating and cooling loads. That's no big deal. But it does present opportunities and risks, as we've seen with respect to already. We've talked about the risks of poor humidity control, poor comfort control. And the goal then of the building science input is to balance the comfort, the efficiency, and the cost, both the first cost and the operational cost. There is virtually no difference between the price of a 50,000 BTU and a 75,000 BTU furnace. I get that. That's not the issue. But there is a cost difference in the ductwork that you have to hook up to a 50 and a 75. That is, a 75,000 BTU furnace moves more air. So now the ductwork has to be bigger. The grills have to be bigger, and so on. And so there's cost there, and there's space concerns. The real cost in equipment is in air conditioning mode. There's it's $500 a ton or more than that, perhaps. $500, maybe half a ton to get a bigger air conditioner. So keep that in mind. So it is about getting the size right, not only at the house level, but at the granular level, at the room size. So I wanted to just show you quickly how to do that. Hopefully you're okay with this. And again, you would choose the design day. You would think about conduction losses through the enclosure of each individual room. You would, in terms of heat loss, and you would think about the air leakage through the enclosure under those various rooms. And of course, you would want to think about the radiant gains through windows. So I'm just going to give you a little quick example of you see that bedroom, top right, bedroom 3, a 5x4 window, 10-foot wall, a 15-foot wall, which means I've got 150 square feet of attic space. You get the idea. It's got 2 exposed walls. It's got 1 exposed ceiling. It's got 1 window. And on the cooling side, in addition to that, we need to understand the solar gain through that window, plus some internal loads. So I'd have to think about the people in that bedroom. Plus, I'd have to think about air leakage and ventilation in both of those cases. In this case, I'm going to say to you, let's assume 10-foot high ceilings. Let's assume a window solar heat gain of 0.3. And let's assume a winter design of 10 degrees Fahrenheit and a summer design of 95. Just so you see some relatively easy math. And remember, we're going to apply these 3 basic formulas. The conduction flows through the walls and the ceiling, the radiant flow through the glass, and we're going to think a little bit about air leakage, and then I'm going to tell you how they actually do it, and we'll see what happens. So here's the spreadsheet, right? You would take the surface area, both summer and winter, 150 square feet, and you're going to go back, wait a minute, that's not exactly 150 square feet. I don't know if you can see my cursor, but the entryway, but we don't quibble over that, or I'm not quibbling over that. Obviously, you should do a click, click, click and figure out the actual square footage, but for this purposes, I'm using 150 square feet. And the temperature difference, remember, is 70 in and 10 out, temperature difference of 60 degrees. In the summertime, the temperature difference is 95 to 75, so 20 degrees. And in both cases, I divide it by 30. And you'll notice, it's 300 BTUs of heat loss, and it's 100 BTUs of heat gain. Not a lot of heat gain. And you go, yeah, but the temperature in the attic's double that. Sure. or maybe it's a 40-degree temperature differential. That wouldn't be a bad number, right? Instead of being 95 in the attic, it might be 125 in the attic. Okay, so I have a 40-degree temperature. Typically, at least on the, so that's where we would put it. And so you'd have 200 BTUs because I doubled the temperature difference. You'd go, oh, I got 200 BTUs. Okay, we'll see the difference here in a second. There you see the walls, the temperature difference and so on. And you'll notice the walls in this case are way more than the ceiling. Oh, because I got more surface area. And so the attic doesn't really play into this much. And then I have the window itself, R3, sort of a typical double glazed low E argon window. That one window is 400 BTUs. Oh, that one window is more than the ceiling, more than the attic. Oh, that's important to understand. So that's just the conductive gains and losses through the window. Now, if you apply the solar incidence, if I said this window was on the south side, I would have 20 square feet times, remember the 50 BTUs, times 0.3. I got 300 BTUs. Wow. In terms of heat gain, only the walls are bigger than that window. That is, the window is almost, that one small window facing south is almost as much heat gain as all of the walls in that room. So the windows are a big deal. Let's turn it west. And now that window is 540 BTUs. You can see why we're not that worried about attic insulation and what the temperature in the attic is. Boy, choose a good window, 540 BTUs on a west face. You can also start to imagine heat loss, heat gains. I wonder if I should be doing lot specific. If I'm building the same house in 4 different orientations, I probably want to do lot specific. Is it going to change the size of an air conditioner? Some of the houses you guys are building, it could change the size of the air conditioner. And that might be a cost savings, might also be a comfort. That's something you're going to have to think about. They're certainly starting to do it in Vegas and so on. They're doing lot specific because the orientation affects the size of the air conditioner. And there's cost savings and there's comfort implications. So keep that in mind. So that was bedroom number 3, that corner bedroom. Oops, sorry. In terms of how do we determine how much air we need to heat and cool, we're going to take that formula. Remember the formula, the third formula, which was the airflow formula? The number of BTUs per hour is equal to CFM times temperature difference times 1.1. If I turn that around and ask how many CFM do I need to add X amount of heat, BTUs, now the CFM that I need is equal to the BTUs, heat gain or heat loss of the room, divided by the temperature difference across the furnace or coil, and divided by 1.1. And what you need to know is a typical, at least for today, a typical furnace temperature rise is 40 to 60 degrees Fahrenheit. That is, a furnace takes in return air at 7 degrees. By the time it comes out of the top of the furnace, it might be at 110 to 120, maybe as high as 130 degrees Fahrenheit. How do you know that? The manufacturer will tell you that. They will actually tell you, here's what the recommended heat rise is across my equipment. Same with the air conditioning coil. Notice that the temperature fall across the air conditioning coil is much less. It's about half. It's 20 to 25 degrees. We can only cool air down to roughly 45 to 50 degrees. So we're only cooling it by 25, maybe 30 at the most. So keep that in mind. And we can use that then. If I told you, oh, I thought I had it, the total heat gain of that room, I'll just go back quickly. So the total heat gain of that room, heat loss, the 300 plus the 1,000 plus the 400, that's 1,700 BTUs. Everybody okay with that? 1,700 BTUs out of that bedroom 3. And then you're going to, well, I got to add air leakage. Right. And here's what most heat loss heat gain programs do. They take the total heat air leakage for the house and they apportion it out to fairly evenly to individual rooms. That is, they take the same, they take the percentage of heat loss of the house and assign that to air leakage. I'm not explaining that very well. Except F280 now says bedroom on the 3rd floor actually doesn't have a lot of air leakage because it's above the neutral pressure plane. So I'm going to say to you, on average, this isn't exactly true, but you'll get the idea. They apportion the air leakage. We don't know the air leakage of bedroom number 3, so what do? We kind of guess, and we estimate. And we say it's roughly 10% of the heat loss of the house, so 1,700 BTUs plus 10% is kind of what it would say. So how much air do I need to heat that room? I need 1,700 BTUs divided by 1.1 and divided by 40. I need 39 CFM. That's how many CFM I need coming out of that register on what day? On the coldest day of the year. On the coldest day of the year, I need 39 CFM. Now, there's people on this call that are immediately going to raise their hand and go, well, wait a minute. The air coming off the top of the furnace was 40 degrees, but by the time I got out to bedroom number 3, what temperature it was. And here's the problem. Heat loss, heat gain programs don't give a lot of thought to that. They actually don't. You can put in factors. You can put in factors that say I need more air, but you can start to imagine if I have a long run that went through unconditioned space. Oops, I'd want to consider that. Look at the cooling loads. The cooling load in this case, facing south, were 866 BTUs, and just magically, it just turns out magically, that it too needs 39 CFM. It has roughly half the heat loss, or heat gain, half the number of BTUs, but it only has half the temperature coming across the coil. So it's, again, 40 BTUs. So that's kind of nice. That bedroom needs about the same amount of heating air as it does cooling air. You can imagine there's other rooms in the house, like the basement. The basement doesn't need any cooling, but the basement needs a lot of heating. Oh, but I have to size the duct for the largest of the two. So we have to keep that in mind as we move through this. So I just wanted to give you a sense of that. This is where we're headed. But now let's think about bedroom number 2. Now we're talking front right, if you will, the house. And now you're over the garage. And let's assume the house turned. Instead of facing north-south, now it's facing east-west. And look at the size of that window. It's not a 5-foot window. It's an 8-foot window now. Oops, what happens to this? It has the same square footage. It's the same 10 by 15 room, but it's got more cold surfaces, more glass, and potentially more air leakage, right? Room over the garage, a neutral pressure plane. Gee, I wonder if air's leaking into this room. And in fact, of course it may be. Air simultaneously may be leaking out of bedroom 3, but leaking into bedroom 2 because of stack effect, because you have a cold garage underneath it. So that's an interesting one. And if I look at this one, you'll have to just believe me on the numbers, but the heat loss just went up to 2,100 from 1,700. So now I need 48 CFM. The heat gain went from 866 to 1,450. Why? Because of that glass, right? The glass was the big deal here. It was a bigger piece of glass, and it was 90 BTUs per square foot as opposed to 50 BTUs. And now look at the discrepancy. That duct needs 48 in the winter and needs 66 in the summer. And so this is where homeowners get concerned. Charlie's bedroom's fine. Melissa's bedroom's always cold in the winter and hot in the summer. It's the same size room. This can't be. So what? And I just did one of these last week. And for heaven's sakes, let's measure the airflow. On the design, let's measure the airflow. I don't have to wait for the design day, right? I don't have to wait for the hottest or coldest day. I just need to know, am I getting 48 CFM out of that vent? Am I able to get 66 CFM out of that vent? That's what I need to know. And of course, you're going to say, well, I need 66 in the summer, and then I need to close it down in the winter. Yes, that's natural. That's normal. That's called being in Canada. But I would say homeowners haven't been told that. Your homeowners have not been told that this system was set up for both heating and cooling, and heating and cooling is different. So you're going to have to balance it. And if they go, well, that's not me, somebody else has to do that, then you'd say, fine. Then I'll sell you a zoning system or something different to get you different performance out of that. And so the classic case here is these high performance houses, end up with smaller furnaces and smaller air conditioners and fewer runs, frankly. I don't need as many heating and cooling runs and fewer return ducts. And the main ducts, return grills, the main ducts end up getting smaller, but we still have to think about getting airflow to that second floor. We have to worry about how are we going to manage that airflow, and that's our next challenge, if you will. So let's talk about some of the risks and opportunities in our next little segment here. And the current HVAC realities are we design equipment 10 to 25% bigger, 10 to 25% bigger than a condition that lasts that 1% of the year or 0.4% of the year, 50 hours a year. And yet homeowners want it to be comfortable every day, not just on the coldest day. And we have ductwork that still leaks at the rate of 25%. Well, 20 to 25%. I should update this slide, at least in Ontario. Alberta, and unless you're sealing ductwork, your ducts are leaking at 25 to 30. In Ontario, let's be really clear, your ducts are leaking at 15 to 20, some of them 25. And you have this problem where you have more and more windows, and that is an intermittent load. That window on the west side is only a problem when Melissa's going to bed. Like, she goes to bed at 8 o'clock, and that's where the sun is streaming in. Boy, during the day, Melissa's room's just fine because it's east face. She needs a whole bunch of air conditioning at night, not necessarily during the day. And it doesn't really help you to say, yeah, but it's cool during in the morning. I want it cool at night when Melissa's heading off to bed. And at least she's going to close the blinds, but unless she closes the blinds earlier, we have a bit of a problem. And of course, homeowners' expectations have gone up, right? The 1 to 2 degrees Celsius, they're 1 degree Celsius, 2 degrees Fahrenheit, and plus or minus 3% RH. We have those issues. But I am going to say there are some great technologies. You guys will recognize, hopefully on the left, duct sealing technologies that can get you down to 2% leakage. The good news is right there in the center, all air handlers now are ECM variable speed fans, ECM fan motors, or the equivalent of, which gives you much better ability to manage airflow. This is a huge win for our industry that those furnaces are there. Yes, they're more efficient, but they also have better airflow, I'll say flexibility. They're not a panacea, but they give you better control. And you do have better control options, which is both a good and a bad. Homeowners want it. Infinite control, but they do give you ability to manage both temperature and humidity. And we do have window coatings that help manage the radiant flows. So we do have some technologies that are helping us improve these performances, if you will. But the comfort challenge, and many of you have seen this before with Robert Bean, so I won't rehash it too much, but just remind yourself that comfort is a function of the air temperature, the humidity, the airspeed, and the one that we've always like to point out is the surrounding surface temperature. And this is most important in that solar gain situation. You're feeling partly the air temperature, and you're feeling that radiant gain, that 4 trillion degrees worth of heat coming from the sun. And I know some days it feels like 4 trillion degrees coming through there. It's not 4 trillion by the time it gets to us, but it is significant. That 90 BTUs per square foot is pretty impactful. 90 candles, little birthday candles, 90 candles for every square foot is how much energy is coming into that space, perhaps, depending on the solar gain. And of course, our sense of comfort does vary, depend on gender and age, and folks who are working with seniors thinking about the comfort level they have. So, and then you've, again, probably seen this before, but you know, in terms of our sense of comfort, the human body transferring heat, 50% of our sense of comfort is associated with the radiation of surrounding surfaces. The good news is we build much more efficient houses with much warmer walls, much warmer windows than ever before, but still, especially in the heat gain mode, we're still seeing that impact of the radiation. Of course, we're not measuring that. We're only measuring air temperature, but we have this huge comfort issue where it's a surface temperature issue that we're worried about. And of course, people have changed. I always like to show my grandchildren, but that's the way my son likes to dress year-round. Summer, winter, shorts and T-shirts, no slippers. And he's become acclimatized to this incredibly narrow band of temperature. I mean, I grew up knowing that you wore flannel shirts and corduroy pants. And he grew up in a household, an R2000 house since 1992, where the temperatures were so consistent, he felt he could live like this. And I've, of course, foisted him on the world, and now every builder that he builds with, he has to meet that same comfort because he's acclimatized to a very narrow band. And so we think about those challenges that we have in our houses. But remind ourselves that the windows and doors, the issue is we put more windows indoors. And over the last 30 years, we've basically doubled the windows in houses. We used to be at about 6 to 8% window to wall ratio. Now we're at 13 to 17%. And it has huge impact on cooling loads is what we need to get to. And you've seen this before. There's kind of the range of choices you can get. And you can get anywhere from about a 0.19 solar gain to a 0.61. 3 times the solar radiation. And if you put big windows facing east and west, if your houses are facing north or south, the effect is cut in half because there's only roughly half the amount of solar gain through a south-facing glass than there is through east and west. But the houses that you built on the east and west that are oriented, the street running north-south, house running east-west, boy, you better be careful about this solar gain that you're getting off this glass. And I just don't want you throwing more tonnage at this because remember, that's an instantaneous load. That load is only there for a short period of the day. So you have this odd circumstance. You're going to oversize for maybe a few hours out of the day, and that's going to mean the rest of the day it's not dehumidifying correctly. So we have to find a way to do this, and you can do it partly by choosing better glass, or you're going to find different heating cooling sources. Is what you want to get to. And just to give you a sense of a 2-story house, 2,300 square feet, all I did is took a heat loss, heat gain, and changed the solar gain of the windows in that house. The heat loss, of course, hardly changed at all. But the heat loss, the heat gain went from 27,000 BTUs, 2.5 tons, some might say 3 ton, to 19,000 BTUs, which would be, in fact, 2 tons, in fact, 10.5 you could do in this house. Because that's, again, an intermittent load. So imagine what that might do for you. And the problem is, again, the 2.5 tons. Even if, well, I don't mind putting in 2.5 tons, that's fine. But remember, that's not the heat gain in the middle of the night. That's the heat gain when the sun is shining on all windows at the same time, which of course never happens. But that's the size you need to put in based on CSA standards. So think about those requirements. So that's a risk, if you will. And then the duct sealing, I mentioned that we're seeing a nice change here. I'll show you some math that we've done some changes. We got this change in the Ontario Building Code. Alberta and New Brunswick, you guys get to be jealous of us for a change. We now have in our code that you have to seal at least the transverse joints. You don't have to seal all the joints. Of course, you should seal all the joints, but you don't have to. And that's the duct leakage used to be at 25 to 40%. You're going to see here in a second where it's gone down. But Steph, I see your face. You had a question.
Yeah, we've had a few questions come in. So are you okay with answering them now?
Absolutely.
All right. Okay.
Well, if you think I can answer them. If you think I can answer them.
Well, let me give you this first one. It's a tricky one. How much would a builder save on system installation, including duct sizing, by doing a blower door test?
Well, obviously it depends on how good your blower door test is. I would say most designers, when I see designers designing, I see some designing at 3.5 air changes, some designing at 4.5 because they want to be safe. And if your house are 1.5, that means if the designer's at 4.5 and you're at 1.5, you've reduced by 60, 70%. Something that accounts for 30% of your heat loss. Oh, that's significant. Now, here's the issue. It doesn't help you much on the cooling side. And I already said to you, the furnace size doesn't get that much smaller, or sorry, not much cheaper. That is, a 75,000 to a 50,000 isn't a lot of money. But if I can reduce the size of the ductwork, all right, now there's some savings. So I'll be blunt. If you know you're building tight houses, or you think you're building, well, every builder should know this. Test your houses. And if they're not tight, okay, fair enough. Tell your designer I built a leaky house and design accordingly, please. But if my houses are tight, I'd like to take advantage of that. And the other nice part about, let's say, downside of air leakage is it too is an intermittent load. And it's really a comfort issue. So I don't have to put in as big a furnace. My ductwork is slightly smaller, so I do save a little bit of money. But I end up with a more controllable house. So will a builder save money by doing a blower door test? Yes. Are those savings significant on the heating equipment? Not big, but they're little bits. And they're going to save more money in other ways. Hopefully that answers.
Thank you. Do you consider solar heat gain in the winter when calculating heat loads? If we lose 400 but gain 300, we are a net 100.
Sure. And the answer is the heat loss, heat gain, the heat loss specifically assumes deepest, darkest night of the year. So no heat gain. You do need to recognize that intermittent loads, the nature of loads, in I would say extraordinary amounts of glass, The problem is you still have to heat it at night. And so, but you do need to understand, boy, I probably need a quick response heating system. That's why, oh, don't get mad at me, those like to do in-floor. That's why in-floor becomes a problem with big windows. Because you geared it up for the heat loss, you got it all nice and cozy and warm at night. And then in the morning, the sun comes out and oops, now the room overheats. And the in-floor, unfortunately, isn't quick enough response. So if you have huge amounts of glass facing south or west, even in the wintertime, you're going to go, I may want a supplemental heating cooling system for that room because it's going to overheat at night, even in the winter. Sorry, overheat during the day in the wintertime, and certainly overheat in the summertime. So, yeah, you have to give that some thought. But the fundamental answer was no. F280 does not count for windows in the wintertime.
Okay, thank you. So when thinking about these recommendations in the context of a MERB, are there resources you can recommend for examining heat loss calculations? And they say, for example, better envelope delivers lower mechanicals, lifetime energy, less volume dedicated to ducting, et cetera.
Yeah, I would say from a heat loss, heat gain perspective, I still feel very comfortable with F280. The fundamentals are there, surface area. You know, I don't, if I'm on a inner townhouse, back-to-back townhouse, back-to-back stacked townhouse, boy, those rooms only have one exposed wall. My heat loss goes down and F280 will capture that. So yes, you would still use F280, in my opinion. There's other programs you could use, but there's no reason to switch off of F280 just because you're doing MERBs. You would just do it for individual suites is the problem, right? And the 201 unit is different than the 301 unit because the 301 has a ceiling and the 101 has a floor. The 201 has a different heating cooling size than the 301 or the 101 suite. So size accordingly.
Thank you. Are you seeing promise in mechanical desiccant dehumidification system as a lower energy comfort cooling option?
Certainly desiccants, this is where it's absorbing moisture. Think of the hull of ships. That's how they've always historically, because you're out at sea, boy, ventilation, dehumidification. They use desiccants and they absorb that moisture and then wait, hopefully absorb enough and wait for it for a time where they can blow it off. They actually heat up that desiccant and blow that moisture off. I haven't seen much of it in residential. We do see it in commercials, highly specific commercial applications where moisture control is far more critical. Typically, we're seeing whole house dehumidification as being the answer. One, ERVs to reduce the load. ERVs are not dehumidifiers, but they do reduce the ventilation portion of the humidity load. Or two, you would think about whole house dehumidification. Or three, you would think about variable speed compressors on air conditioners that can do a dehumidification cycle. Those are the three technologies for managing moisture in summer.
Lots of questions keep coming in here. So how is west facing living architecture tree shading valued?
Oh, I'd a girl or whoever asked. Sorry, boy, girl.
Chris.
Thank you.
Yeah, it's a Chris.
Well, but it could be either, right?
That's right. Yes.
That's fine. I should be gender neutral.
That's right.
Thank you for your question. They've asked a good question, if I can put it that way. The answer is yes, you can account for shading. You absolutely can say, I've got deciduous trees. You can put that into the programs, whether it's overhang, outdoor shading, and you absolutely, in F280 can say it's well shaded. And that's absolutely critical to know. I've been to houses where they didn't know the place was going to be shaded. It was a infill house built in Forest Hills, beautiful area, right? 10,000 square foot house. It was sized as if there was no shading whatsoever. And of course, was put into a Forest Hills in Toronto, which was full of beautiful trees. And it was oversized by double. And the occupant, the owner of the building, who had built a 10,000 square foot house in Forest Hills, you can imagine, was pretty adamant that he wanted better temperature control. And he was sweating terribly. And he said, I got two choices. I can either lose weight because he was quite a heavy-set man, so I won't be affected by the moisture, or I could fix this air conditioning system. He looked at me and he says, "What one do you think I want you to do?" He said, I didn't bring you here because you're a fitness expert. I brought you here because you're a roof expert."
That's a fantastic story.
we literally had to decommission half of his conditioning. He had a
Mm.
10-ton system and he only needed 5.5. And we had to find a way to decommission and rejig to get rid of 4 tons of air conditioning out of his house. And this was years ago, so we didn't have access to good dehumidifiers. Somebody said, just put in a good dehumidifier. There wasn't good whole house dehumidifiers at that time.
Well, especially for a house that size.
Yes.
So another question is, does oversizing lead to thermal comfort issues from increased drafts?
Well, good question. I would say a reasonable question. I think you're talking about airflow distribution, perhaps. I'm going to presume that, and I'm going to get to that here in a second. So let's leave it at that.
Okay, sounds good. So Sarah is asking for something, and I'm going to ask her to put this idea down on the survey that's going to pop up at the end. But she is enjoying this session, and she says, "Can you offer a similar course that is focused on sizing heat pumps, ducted and ductless?"
Well, of course, and the answer is yes, because pumps do have. What's the difference? The big difference with heat pumps, ducted, is that remember I said the temperature rise across the furnace is about 40 to 50 degrees. Heat pumps, no. Heat pumps have much lower, especially on cold temperatures outside. Air source heat pumps specifically have lower temperature rise, which means I need more air. Heat pumps, typically, you need more air to deliver the same amount of heat because you have less temperature rise. Nothing wrong with heat pumps. They're great, except instead of a 40 to 50 degree temperature rise, it might be a 20 to 30 degree temperature rise. Oh, so I need about roughly, not quite twice, but I need more air in the duct system. So yes. So the good news is you're going to make better houses, which means I can put less air. Now I need more air because and I end up roughly where I'm at. But yes, we should do that as a course.
And the last question is, our builder will not be doing a blower door test. Does it make sense to do a blower door test a year after the house is built and then reconfigure after?
Sure, I would say if builder's not doing a blower door test, then I would say pick a number and say to the builder, if you're the designer, say to the builder, look, I've designed this at 3.5 air changes because that's what the code says you should be at. If you're not, then it's on you. If it's higher than that, I'm designing for that. And that's what you'd put. That's literally, you'd write down on your information sheet. There is a sheet in F280 that says, here's all my design assumptions. I've assigned 3.5 because the code says you should be at 3.5. That's why builders need to be blower door testing houses. That's fine. But yes, after the end, if you're finding the system isn't working, one of the first things you do is do a blower door test. If you're finding it's too cold in the winter, the whole system won't keep up. Not an individual room, but if you find the whole system won't keep up, then do a blower door test and see whether you sized it correctly, if you will.
Okay, that's it.
So I'll move on. Thank you. And now I am running out of time, but we'll be fine. So the duct sealing is kind of nice. This was a survey we did after the new code. Look on the right-hand side. There was the second last column is the total flow. And we measured the flow at the furnace. We measured the flow out of individual grills, and we watched the difference. And the difference was 18 to 20%, or I'll say 20 to 25, some as bad as 30%. So when I say duct leakage, you'll see some really good ones there, 2.4%, so that's great. But it's all over the map is the point, and I'm going to encourage you to get this under control because that room over the garage needs 66 CFM. And if you're losing 20% along the way, and wouldn't you know it, that's the longest run, so it loses more than the one going to the dining room. Duct leakage doesn't hurt you in the dining room, but it sure hurts you in the room over the garage where the air is going through a long duct and out through the insulation and so on. You want to get your duct leakage under control. So, of course, there are technologies that will do that. I think I have one slide out of place. There's a technology called AeroSeal, which I'll come back to, that could get you down to 2 or 3% leakage overnight. U.S. is most 28 states are now doing duct leakage testing, even Minnesota, much like us, and their requirement is under 10%. So think about getting better duct leakage. But let's talk, and sort of the rest of the period here is thinking about distribution to get proper conditioning. And there's that bedroom number 3, right? Remember bedroom number 3? Look where the thermostat is, and bedroom number 3. The thermostat is seeing, well, basically, it's seeing a kitchen and a fridge and a whole bunch of kids and TVs. It's hardly seeing any outside walls. And bedroom number 3, meanwhile, is seeing a cold floor, a cold ceiling, 2 cold walls, and a big cold window. And in the summertime, it's seeing hot elements as well. So imagining that comfort challenge because of those elements, and then superimpose on that potential duct leakage, the temperature loss of that duct as it goes through the garage, and the thermostat location makes this room really, there, I'm out of sync. Sorry, I'll get rid of that. Oh, my apologies. I had one slide out of order. So let's go to bedroom number 2 here. And let's talk about that heat loss, heat gain, 48 and 66 CFM. Now, the good news is, what if I improved the performance of that room? That is, if I doubled the wall insulation, cut the solar gain in half, cut the air leakage, say, by 70%, you'd have roughly half the amount of heat loss or heat gain, which means now I only need 24 or 33 CFM out of that room. So 1, fix your duct leakage. Sorry, my apologies, Steph. I somehow a slide flipped on me. I'll go to this one. Let me do this aero seal. Notice the graph on the right-hand side. I'll highlight that. There's what happened to duct leakage over 28 minutes. It went from about 20% down to about 2% duct leakage. And I'm going to say the room over the garage would really love this. Houses become much easier to control when you do duct sealing. Look at this room. The airflow before and after duct sealing went up by roughly 20%. So this happens to be my own house in the master bedroom. Just by duct sealing, I was able to get better flow to the end runs. So I'm just going to encourage you that room over the garage become much easier to do if my ducts are sealed. Put that on your list of things to investigate is what you'd like to get to. Notice the total airflow that actually got to the house, to the rooms I actually wanted, went up by around 25% as well. In other words, I had 20% duct leakage, so pretty powerful. Okay, so we're back to this room and thinking about bedroom number 2. My apologies for being out of order. But thinking about how do I make sure I get that 48 and 66? And you might say, well, I could put 2 ducts into that room and close one off in the summer, close one off in the winter. Sure. Fundamentally, I need to be able to balance the house. Bedroom number 3 has the same size duct, same square footage. I need to be able to say to the homeowner, or when I first build the house, this one's facing west, I need more air. So builders should be, and mechanical contractors, if you're not going to do lot specific, orientation specific heat loss, heat gains, then you probably need to be doing commissioning and figure it out, because the house on the south side of the street is going to need different airflow characteristics than the house built on east-west. So I'm going to put it on builders that if you're going to do high-performance houses, you probably need to be commissioning the HVAC system to set it up for this house built to this specific orientation. And then overall, do yourself a favor, make your houses more efficient. And now it's far less problems getting heat out to those specific rooms or specific areas. That's really the lesson. And notice that the difference is now only 11 CFM between summer and winter. It's much easier to manage that than the 20 or 25 CFM that you need summer to winter when you don't have a high performance house. So it's an opportunity, but it's also a challenge, if you will. So getting that proper distribution is what we're looking for. And that the next issue is the design of grill. There's 2 different terminologies or technologies. You want a grill to either throw the air or you want a grill to spread the air. When we were in heating mode, that room on the second floor, we're trying to bathe the walls. We like spread. Spread is done for heating. In cooling on that second floor, we want the air to get up past our head level. So we actually want to throw the air. So interesting enough, most of the residential grill folks don't have any information on this. You actually have to go to a commercial style grill to get throw and spread information. But I'm going to encourage you to give this some thought. So I would say design for slightly higher pressure in your duct system and design for higher grill velocity, of course, without creating noise. And you're going to say, what level is that? And it's got to be less than 900 feet per minute. How do I know that? Because I've measured it. And more importantly, I'll say it this way. ASHRAE says not over 900. HRI says not over 900. And every homeowner I've ever measured who tells me the grill is noisy, it's always over 900. So lower is better, but you can design for more. But the key is to get that, decide whether I want throw or spread in any particular application. And rooms on the second floor, well, frankly, in cooling mode, you really would like throw versus spread. You like to get that cooling up. Now, are there grills that can do both? And the answer is yes. You can get adjustable grills that can spread in the winter and throw in the summer. You can get adjustable grills. The next question I get is, what about return air? Would it help me if I had return air in that bedroom? And the answer is, test the pressure across the room with the door closed and the door open. If the pressure changes by more than 3 to 5 pascals, then you need return air. Otherwise, you don't. And here's why I can say that with a high degree of assurance. How much air did we need to heat that room? Let's call it 40 CFM. How much heat do I get by taking air out of that room? And the answer is none. If I take out 70-degree air and bring in 70-degree air, I didn't add any heat to that room. Return air does not help you heat or cool a room. Return air is simply a pathway for the air that you put into the room to get out of the room. That's all it is. So all I need to know is, did the pressure change in the room? And if it did, then I need return air. I just did this at a house. They'd been arguing for years, well, a year and a half. Need to put in return air, need to put in return air. They're worried about privacy issues and noise. They didn't want to put it in. I went out to the house, I measured the pressure, it didn't change. The airflow didn't change when I opened the door or closed the door. So return air is not going to help. If the supply flow doesn't change with the door open or door closed, return air is not going to help you in that room. Now, let's be really clear. I'm not saying you don't need return air. You need return air somewhere. You need the air to get back to the air handling appliance. You just don't necessarily need it in every specific room. And you can determine whether you need it, at least after the fact, by simply doing this measurement. And the reason for this is a fan can blow air 30 times farther than you can suck it. If you're trying to heat and cool a room, it's all done with supply. It's not done with return. Supply is more important than return. You need return. It just doesn't help you heat or cool a room more by putting in more of it if you already have enough of it. And that whole idea of that spread versus throw, I clearly have these slides out of order, but you'll notice this room on the right-hand side needs more throw. It needs the air to get up higher. It worked fine in winter because of the natural buoyancy of warm air, but in summer, that 350 feet per minute just isn't enough. I need to get to 550, 600, maybe 650 to get that throw up and over, or use a different grill, summer to winter, or an adjustable grill is what you want to get to. And I did mention, just in a few minutes remaining, that maybe we want to start designing for slightly higher static. Why do I say that? Because we now have furnaces with ECM motors that can get us a little higher static pressure, a little more oomph to get that air out to the room over the garage. So I'm good with that, especially when I air seal the ducts. Actually, when I air seal the ducts, the pressure is going to go up, which is nice. The pressure in the duct's going to go up because the air actually has to go all the way to the end run. So you're going to like that. What I don't want you to do is on the right-hand side. We see people using the high velocity, high static systems as a panacea. And I find them to be noisy and they're not working because people are taking shortcuts. They're not sealing the ducts. Notice the knuckles on that elbow. None of those are sealed. And you go, we don't need to seal an elbow. In a low static system running at 0.2 static, maybe not. But when you're at 1.2 inches of static, guess what? Every one of those elbows leaks. So you need to do a better job of sealing if you're using the higher velocity ducts. And I'm going to say to you, you're probably going to move towards zoning. A room over the garage, the second floor, whatever, probably needs, in high performance houses, you're going to get to zoning. Or you're going to move to supplementary heat pumps. I see this as a technology that you're going to be using. Not necessarily even a supplementary. You may be using these technologies to heat entire houses, certainly in the MURBs. Boy, you don't need much. So why aren't we just doing single room when I know the bedroom, or they only have 2 or 3 exposed walls in the entire place? Why am I not doing these kinds of heat pump based systems? And that's really the finish to this is be more creative. Zone systems on the left with traditional furnaces and variable speeds. In the middle, thinking about the mini split systems. On the right-hand side, thinking about radiant heat in different formats so I can have quicker response or slower response. Radiant heat's perfect for a basement. Radiant heat in a towel warmer is great for a bathroom, quick response time, or air handlers. So those are the new options that you're going to find really, really useful. And then in about 1 minute I have left, I'm going to say commission your systems. And when I say commission, here's what I mean. Measure duct pressures, see where you're at. Measure airflow and pressures at the furnace. Measure airflow at registers. And most importantly, measure and verify refrigerant verification. Air conditioners are notoriously bad in terms of when do you charge them up? You need to do a commissioning of your air conditioning system at the start of heating season. You can't possibly do an air conditioning setup in the wintertime. You can't set it up correctly, or even in the fall. So you should be adding verification or to your systems. So as we finish off, this is the opportunities. We're going to be seeing more heat pumps. We're going to be seeing still the efficient backup gas. We're going to see heat pump water heaters. But most importantly, in my perspective, you're going to see zoning. You want to think sealed ducts, and you want to think smarter controls that give you dehumidification. We'll do that in a separate session. So in the high performance houses, no compromise. Efficiency and comfort. You're going to have to go a little further. The loads get smaller, both heating and cooling. Air leakage, of course, is a significant factor, but great opportunities for new HVAC sizing. Your savings comes in the sizing comes from the size of the air conditioner and the size of the ductwork. That's where the savings comes from in terms of capital cost. It also saves you because of less warranty callbacks because of comfort. Commission your systems. Hopefully that was useful. I want to say thanks to Susan again on behalf of myself of Enbridge Gas. You guys are always so generous to do this training session. Hope folks found that of use, and I know I'm 1 minute over.
Very well done, Gord. And yes, in fact, Chris, who had asked a question earlier, said, thank you. And it's a great session and the best use of an hour in a month. So excellent. Okay, well,
we have one.
Excellent. Okay, well, thank you. And as Gord said, we do have, and I'll just share this real quickly so you can see it. We do have a session next month. So we do these every month. So the next one is June the 17th at 1 o'clock from 1 to 2:30. And it will be both Gord and Andy, and they are speaking specifically to humidity control and the three key principles every builder and homeowner needs to know. So that will be excellent. As Gord said, thank you so much to Enbridge for sponsoring this webinar series. And I will be sending out a resource email afterwards that has Gord's slides in a PDF format, as well as a link to the recording. And when I close the session, you'll get a little box that pops up that has the SurveyMonkey link. If you could share your thoughts in that, that would be very helpful for us. So that's all I have, Gord, and I will see you next time.
Yes, and I'll fix these slides.
Excellent. Okay. Thank you, everybody, for attending, and we will see you on June 17th. Thanks. Bye.